Yes.
This meeting is being recorded.
All right. I'll go through it pretty quick and then we'll have plenty of time to chat. So I'm going to be talking today about ROS, Robot Operating System. A little about myself. I'm Andy. I'm a novice hacker. I'm a field engineer for Agilent Technologies automation products. I'm a tabletop RPG developer, and you should definitely check out our game, which is fittingly titled Fully Automated, available for free to download at fullyautomatedrpg.com. You'll notice I am not a ROS expert, so if at any point in this presentation something sounds dumb, assume it's my own mistake and not on the part of the developers for ROS. What we'll talk about today is pretty straightforward, which is what is ROS? What is its use? Then coming back around to really what exactly is ROS? And then some discussion. Let me know if you have any questions. Feel free to interrupt throughout, but you got to speak up because I can't see anything. The slide takes up the whole screen. So the first thing it says on the website is that Robot Operating System is a set of software libraries and tools that help you build robot applications. Elsewhere on the website, it says ROS, Robot Operating System, is an open-sourced software development kit for robotics applications. ROS offers a standard software platform to developers across industries that will carry them from research and prototyping all the way through deployment and production. I would liken it to how I think many of us, I'd ask you to show your hands, but I will say I can't see anyone. But who here as a child was enamored with the kind of sci-fi trope of like kid builds robot out of parts from a dumpster, just scavenging like boards and cameras and makes a robot friend, right? This is sort of a project intended to make that possible because in real life, you can't just take a microphone and a computer and plug them together and get everything to work the way that you want it to. It takes a lot of integration. So what does that look like? It's often summarized as a combination between plumbing, tools, capabilities, and community. On the website, it says that plumbing is described like this. At its core, ROS provides a message passing system, often called middleware or plumbing. Communication is one of the first needs that arise when implementing a new robot application, or really any software system that interacts with hardware. ROS's built-in and well-tested messaging system saves you time by managing the details of communication between distributed nodes in an autonomous publish-subscribe pattern. We'll go into that in a minute. Scrolling down the page, we see a description of the other elements. Tools. Tools are the things to build applications efficiently. You need good developer tools. ROS has them, including launch, introspection, debugging, visualization, plotting, logging, playback, etc. Capabilities. The ROS ecosystem is a cornucopia of robot software. Again, we'll go into all of these with a little bit more detail in a moment. And then finally, community. The ROS community is a large, diverse, and global community, from students and hobbyists to multinational corporations and government agencies. People and organizations of all stripes keep the ROS project going. Who here has heard of ROS, by the way? Okay, I can't see you again, but that was part of my notes. So a few words on the community. This project is 10 years old. It has 8,000 contributors to their repository, 31,000 users on their Stack Exchange, and their last year's conference drew 700 attendees from 42 countries. And I say all of this just to emphasize that, when we talk about open source projects, oftentimes it's little more than an idea, but like this is a real project. You know what I mean? This is like up there. This isn't exactly Python, but we're really working with like a very serious collection of people and programs and structures. It's all managed, by the way, underneath Open Robotics, which is a nonprofit located in the Bay Area with like a corporate subsidiary that has partnerships with a bunch of like tech companies. So it's fairly independent, but also tied into the larger robotics world very heavily, for both better and for worse. So that comes back to the question, what is ROS? And, we have this definition, ROS equals plumbing plus tools plus capabilities plus communities, but that still kind of leaves us like, you kind of need to see it, right? So I'll tell you the way that I found out about ROS, which is I'm a big fan of James Bruton. He's a YouTuber. If you guys aren't already into James Bruton stuff, he runs a channel, X Robots, and I highly recommend it. He has done a bunch of really wild robotics projects, and a bunch of them have used ROS. And so in 2021, I wanted to work on a robot in part because I was trying to make the transition from working at the bench to working in automation. And I thought, building a robot would be a great way to get confidence and have something to show, employers. And so I was working on this robot. The name is Bellamy Crashbot because this was developed with a group of friends at a local hackerspace called Crash Space in Los Angeles. And you can see that Bellamy is a Roomba with a mast, with a Connect, like an Xbox Connect camera, and a tablet for input, running on a Jetson Nano mini computer, and a bunch of other things, kind of hacked together. So that brings us to the next point, which is like, what is ROS's use? What does it look like in practice? And to give an example, this is what Crashy's sort of stack looks like. On the left, you can see in blue all of the things that go into it, all the inputs, which include both human input and also sensor input and things like wheel encoder data. And then on the far right, we have the outputs, the things it does, its response to queries, its behavior, its driving. And in the middle is all of the decision making and processing that's going on. And this is all running on ROS. Now, a crucial thing is, as I mentioned, ROS is not really an operating system in the conventional way. It runs on Windows and on Linux. And you can see this is a screenshot of one of the programs that we use. This is a mapping and navigation program that's doing real-time location identification from the environment. And it uses this to build a point cloud map in 3D of my brother's apartment. And I think this all just looks really cool. And the main thing I want to emphasize here is I cannot develop this. I didn't create any of this. This was only possible because a bunch of developers have produced something really impressive, right? So that brings us back to the plumbing, the tools, the capabilities, and the community. Hopefully it's starting to make some sense. How does this work, right? This is where we really get into it. And I would say this is the sort of the heart of the messaging system, the plumbing, okay? And the way it works is that there is, on this, you have a computer, you install ROS, and then you run a bunch of programs, and each of those programs are nodes. The nodes are each dedicated to doing some kind of task, right? And then those nodes communicate among each other with this very clever messaging system. The basis of the message so far. Does anyone have any questions so far, real quick? I can't hear or see anything, and I don't know if I'm still connected to the meeting. Can someone just give me keep going?
I can hear you as long as you can hear
great,
us.
Great.
Keep it going.
Right. People don't have
Awesome.
questions. They shook their heads.
So what you can see here is that we have a node that's publishing to a topic, a message. And then we have other nodes that are subscribing to that topic. And that's how they get information from the one node to those other nodes. At the same time, we also have this little box labeled service, which is similar to a node, but with extra features. And we'll go into that in a moment. But for now, let's just talk about topics, okay? This is a graph of a demo system, like a template that you use in tutorials for what's called TurtleBot. And at the far right here, you can see the one labeled /teleopturtle. That is a node, and that's the node that is taking input to control this little robot. It publishes that input to a topic called command velocity that is within the Turtle1, environment. And then that is subscribed to by a node called TurtleSim, which is just simulating the output. But this would be, if you wanted to build a physical robot, this would be receiving that command velocity and telling the motors to move. And then that publishes to a topic called action feedback, which is interpreted by the teleopturtle node and used to decide whether it's time to, for instance, stop sending it instructions to move forward, right? Now, here's where it gets really cool. What you're looking at down here is a replica of a command that you could issue in the command prompt in Linux. You type in ROS2 topic, and you're saying to ROS, I want to do a topic action, specifically the action echo. And I want to apply it to the topic command velocity located under turtle. And you can see the output is linear, X, Y, Z, angular. This is a text readable display of what's in that topic. And the crazy thing is, if you go to the topic, I believe you can open it with like a notepad or something, and you can see this in a human readable format. This is just the instructions for how to drive in each of these parameters, right? This is the command velocity in a readable format. And similarly, if I were to type in ROS2 and say, I want to do something with a topic, but instead of echoing the contents of the topic, I want you to give me the info on the topic, and it's the same one, okay? You can see it says type, geometry messages, message, twist, publisher count, 1, subscription count, 2. This is information about who's connected and what format it's in. And this is where I really want everyone to take a moment and sort of see if all of this is starting to come together. Because in order to send information between the input device, which is a node called teleop turtle, and turtlesim, what we are doing is we're essentially just writing text to basically a human readable text file in a standard format, and then having a downstream node read that in, right? That is the basis of ROS, and it almost sounds stupid. Like, it feels too simple. You're like, how is that? That's the big innovation. But no, seriously, if you think back to all the stuff that we discussed at last month's meeting about how do we create standards, how do we make interoperability, how do we do all these things, this is basically it, is a framework of communication with standard formats. So from there, we can go further because we get I need to get to the next slide. It seems like
Andy, before you go any further,
yeah,
can I just ask a question about
of course.
Where we're picturing these things? So these nodes. So I'm understanding the architecture as there are nodes that communicate back and forth with messages, and those messages are using like pub sub over topics. Is the idea that the nodes are physical machines? Are we communicating over a network, or is this more like all within one device, and it's just using like threads of communication? Like I'm trying to figure out, like, is a node a computer, or is a node a processing thread, or is a node some third thing?
That is a great question. The answer is it's closer to a thread running on a computer, but it's extremely flexible. You can, and this is what we did when we were building this robot, you can, for instance, the Roomba has a lot of onboard processing. That is doing its thing, and then it is sending information over serial, and the serial connection is essentially forming its own node, and then the ROS is sort of interpreting that serial information and translating it into the appropriate formats and publishing it as topics for the rest of the system. We have, for instance, a separate battery system, and that is a physical component, but it also is it's running, I think, on like an Arduino, and it's sending communication over serial. And then that information, again, forms the basis of a node. We have a communication system for communicating in and out via Slack. That's not physical, but again, it's a node where we have a Python program that is, using standard libraries for sending information to Slack and receiving it. And that's another thing I'll point out that's really wild about this is this allows for communication between programs, even written in different codes, right? You can have a Python program, and as long as it's writing in the same format that this other C++ program is expecting, they're sharing information through a topic, even though they're in totally different languages, which is another thing that I think is kind of wild, right? So if we take this and we move further, the next thing is services, right? And a service is essentially a kind of specialized topic. A service, whereas a topic would be like just taking an information like a temperature reading and just publishing it consistently, a service is a call and response between a service client node and a service server node. Sorry, it went to the next slide accidentally, but I don't want to go back. This then brings us to actions. Whereas a topic is just constantly giving us information like temperature, a service is doing things like maybe telling, you could say to a robot, hey, report the current load on a joint, right? That's not information that you probably want to have constantly being broadcast, but you might want to have a way of inquiring, and that's what it does, is it asks and then gets a response. And then actions are a a means of control that use services and topics to initiate a request. And whereas a service is just instantaneous, let's say you wanted to tell an instrument to go do a task and it takes a minute or two. Let's say you want to tell a robot to go get you a beer from the fridge. You want to be able to get progress updates. You want to be able to interrupt it midway through if you decide to, you want to change your order, right? So this uses a whole framework to use a service to initiate the action, topics to communicate throughout the action, and then a service to conclude the action, right? So I'll just take a moment and I want to give an example of like how this can be implemented in a way that I think is kind of cool. All right. Tell me, can you guys see this video that I ended the sharing. I got to start. No, I didn't. You guys can see this video
I can see it.
playing, right? All right.
Yep.
I'm just going to play likes of it.
All right, go ahead and walk forward about a meter and turn 15 degrees to the left.
I'll move forward 1 meter and turn 15 degrees to the left. Please confirm.
Yeah, it's safe. Go ahead.
So this is only a minute long, but I think time is valuable. So I'm just going to show you that so that we can continue discussing it, and you guys can watch it, later if you want. But if it wasn't apparent, what you're looking at is a JPL package for ROS that adds a large language model, speech to text, framework so that you can give natural language commands and it'll implement the actions on this, mobile robot, right? And that's the kind of thing that I think we all really would say is sort of the textbook example of what good open hardware software integration looks like, right? Where they've designed this thing and it plugs into this whole framework so that you could really execute any of the actions that the system is capable of using this large language model. And if you watch the video and look closely, you can see, for instance, it'll say invoking inspect and describe camera feed with robot name, waiting for image on topic, spot 1 camera front color. The logic starts to make sense. And oh my goodness, how easily you can look under the hood, right? Not to say that any of this is easy, but like when I actually started working as a field service engineer, this was a thing I really routinely encountered, is so many of these closed systems are so hard to troubleshoot. Whereas with this system, I mean, you can also have all of these broadcasting actions getting saved to all sorts of data loggers, and you can pretty much see every command the system's running. And if you, for instance, find that something's happening a little too autonomously, you can break that into its own node and have a node dedicated, for instance, to that task. And now you have greater ability to influence or control or supervise it, right? So that brings us back to, what is ROS? ROS is a set of standards for formatting commands, feedback, and sensor inputs between components in a system. It's also a collection of existing programs and libraries that have been made using these standards, including control programs for initializing and managing all the interoperating systems and programs and subroutines. And it's a developer community, a really robust developer community. So now, hopefully, you're like, oh, I get it. ROS equals plumbing plus tools plus capabilities plus community, right? Now, one issue, though, is that I was surprised that it doesn't, not a lot of people have seem to have heard of this in our community. And it seems the reason why, as I dug in deeper, is just because its applications are so heavily tied into autonomous mobile devices. It's not really heavily represented in, I mean, there doesn't seem to be anyone really using this for integrations in the lab. I asked someone online and they said they thought Multiply Labs might be using ROS. And I sent an email and I haven't heard back. But if anyone knows anything, definitely check. But hopefully it should be, apparent where I'm going with this, which is, what if we were to apply this to laboratory automation? What would that look like? And so I'm just reaching the end of the presentation, and I'll open it up so that we can all discuss this in a roundtable fashion. But imagine we have a gripper, we have a liquid handler, we have a plate carousel, and maybe the plate carousel is inside of a temperature humidity controlled environment. We've got spectrophotometer or some other data collection device. We've got plate sealers, peelers, labelers, and now we've got, you know, the sort of the physical integration. What would the framework look like if we tried to apply RAWs to this? I think we might have nodes for the various instruments. We might have nodes that manage data collection, perhaps a node that's sort of specified for the input and interface, both physical, like on-site human machine interfaces, and perhaps the like remote kind of information communication. We'd probably have some sort of master control for scheduling, something for tracking the storage of plates and reagents, maybe one for just monitoring the emergency stop. And then I think it would make sense to have something like a system monitor that is primarily based on machine vision combined with feedback from the various systems that kind of reports if a plate gets dropped or if something's going on that's unusual, right? And so, yeah, I'm going to wrap up here and we'll all talk about it. But like, as you think about what you need in automation control, I'm curious if people see a place for something like RAWs. And if you do, or if you're just interested in getting more experience with this type of thing anyway, I would suggest you go to the RAWs website and follow the links to get started and just sort of see if this might provide something that's interesting to you. And yeah, that is the end of the prepared notes. I'm going to pass back to Tim to sort of moderate a discussion.
Fabulous. Well, first things first, let's give some applause and thanks to Andy for this great talk. I mean, I feel like I learned a ton actually. Get some emojis going on in the chat, please. Great work, Andy. I'm gonna stop the recording.